welcome back to my next video, guys. In this video we will continue on the chapter electric charges and fields. In today's topic we will learn about the concept of electric field. Let us consider an electric charge Q located in space. If we bring another charge Q not near the charge Q, then what will happen? The space surrounding an electric charge Q in which another charge Q naught experiences a electrostatic force of attraction or repulsion is called electric field of the charge Q. Intensity of electric field. The intensity of an electric field due to a charge at a point in space may be defined as the force experienced by a unit positive charge to be placed at that point. In simple word, we can say vector E equals to vector F divided by Q naught, and symbolically Q naught limits tends to 0, then we can write the relation as vector E equals to limit Q naught limit to 0 vector F divided by Q naught. Now we will discuss electric field intensity due to a point charge. First, let's draw the diagram. Suppose an isolated point charge of plus Q coulomb is placed at a point O in a medium whose dielectric constant is K. Then, according to the Coulomb's law, the force acting on Q naught is F equals to 1 4 pi epsilon naught K Q naught divided by R square. Therefore, the intensity of the electric field at point P is given by E equals to F by Q naught. Where F equals to 1 by 4 pi epsilon naught Q naught divided by R square. Simplifying this, we will get the result 1 by 4 pi epsilon naught Q by R Newton per coulomb. For vacuum or air, K will be 1. Therefore, E will be 1 by 4 pi epsilon naught Q by R square Newton per coulomb, where 1 by 4 pi epsilon naught equals to 9.0 into 10 to the power of 9 Newton meter square by coulomb square. In vector notation, we can write E vector equals to 1 by 4 pi epsilon naught Q by R square unit vector r, where r is the unit vector pointing from the point charge towards the test charge. Now we will discuss about the intensity of an electric field due to a continuous charge distribution. If a charge is not a point charge but is distributed continuously along the length of a wire or over the surface of a conductor or throughout the volume of a body, then we can ignore the quantum nature of charges and imagine that the charge is spread in a continuous manner. The first type of charge distribution is linear charge distribution. For that, first we have to draw the diagram where O is the origin and P is the point, and vector r1 and r2 are the position vectors of the element dl. Let dl be an infinitesimally small element of the line charge. Then the charge on the element dl is dq equals to lambda dl. Consider that a test point charge q naught is placed at P. Now the force on q naught due to charge dq equals to lambda dl on the element dl is given as d vector f equals to 1 by 4 pi epsilon naught q naught dq divided by r21 square unit vector r21, where r21 vector is the distance of q naught from the element dl and unit vector r21 is the unit vector pointing from lambda dl to q naught. Then the total force on the charge q naught due to the whole line charge is given by integration over the entire length, that is vector f equals to q naught by 4 pi epsilon naught integration lower limit L lambda dl r21 square unit vector r21, which will be later on represented by E. Now let us come to the second continuous charge distribution, which is also known as surface charge distribution. For that we have to first draw the diagram and then understand its equation. Where r1 and r2 are the position vector and OI is the origin, and r21 is represented as vector r2 minus vector r1. Let there be a continuous charge distribution of charge over a surface with surface charge density charge by surface area sigma. Then the charge on that small element will be given as dq equals to sigma ds. Now the surface charge by the element will be given by d vector f equals to 1 by 4 by epsilon naught q naught sigma ds divided by r21 square unit vector r21. Then the total force on q naught due to the whole surface charge distribution is given by F equals to q naught 4 pi epsilon naught integration sigma ds r21 square unit vector r21, which is later on represented by E equals to vector F divided by q naught. Now let's move on to our last type of charge distribution, which is also known as volume charge distribution. Again, to understand this, we have to draw the diagram first, and as the name suggests, this charge distribution will be represented by a volume the charge of the unit volume will be represented as rho, and thus charge on an infinitesimally small element of volume dV will be given as dq equals to rho dV. Where r1 and r2 are the position vectors of the element dV. Then P is the point. Then the charge due to the volume dV is given as d vector F equals to 1 by 4 by epsilon naught q naught rho dV divided by r21 square unit vector r21. The total force on q naught due to the whole volume charge distribution is given by the total charge q naught will be given as vector F equals to q naught divided by 4 pi epsilon naught integration rho dV divided by r21 square unit vector r21, and E vector equals to F vector divided by q naught equals to 1 by 4 pi epsilon naught rho dV r21 square unit vector r21. If you haven't subscribed our channel yet, please make an effort to do it, and if you like this video, please share it with others so that others can get benefited. And lastly, thanks for watching.